in case you hadn't found them, in course information, I've got a thing saying Mike's information, which I will be updating in a little bit or at some point with some more information. Number one, my office hours are listed here, and what I'm going to update it with is a virtual link. So you will be able to sign in virtually. So I will try and set it up and have it live so that if you have questions, you can sign in virtually if you're off campus. Does that make sense? So I will still be physically in Library 228, but the virtual option will be there if you want to. The other thing, actually I can just do it right now. The other thing is I'm updating office hours. So you are now the first section to know those official, or to have those office hours published. Friday from 2 to 3:45. Maybe a little bit earlier if I feel like I got a bunch of work done that day, but I doubt it. So 2 to 3:45 on Friday, I'll also be in there. Make sense? Okay, I want to make sure you guys knew where it was at. Which then takes us to the Unit 1, lecture recordings. I'm putting all the lecture recordings in here. Remember, Wednesday failed for our class. I apologize. So you've got Tuesdays, technically Thursday's lecture, okay, and then this is Tuesday's lecture, which was a lecture yesterday. Okay, because of the holidays, sorry, I think I need to move a little bit faster. I think I actually need to get you guys out in front of Tuesday, not behind. Make sense? Okay. That said, what we'll do, how do I start this thing? I swear I'm not that old. A little backwards review. For molecules, in order to react, they have to collide. So we need proper orientation and energy for that collision as well. Okay, this was the example with the pen cap. Okay, trying to put a pen cap on a pen, okay, I can smash them together as much as I want. The pen cap doesn't go on until I actually orient properly. Even then, I also have to smash them with enough energy to force them to make that connection. So both of those things are contributing factors. Okay, we'll come up to it a little bit again today. But for an individual reaction, do you think the orientation changes? Because we run a reaction, we're running thousands upon thousands, millions upon billions of particles. Is the orientation going to be different to cause that same reaction for each of those collisions? Or is it going to be the same? Said another way, if we go back to the pen cap, right, and I want to cap the pen, is it possible for me to change the orientation in which these two particles come together? Or is there only one orientation where I actually get to connect? You know what I mean? There's only one orientation, which means for an individual reaction, that orientation is constant. That becomes an important feature. How about the energy? That minimum, again, is going to be constant. It's not going to change throughout the course of the reaction. It's going to be constant. That's an important kind of feature that we will deal with, because ultimately what are we trying to do is quantify a lot of these things. And if we're going to quantify them, there's things that we need to be aware of on what can change, what variables can change, and what things should remain constant. This is known as, I forgot the button up here, collision theory, right? Right, so we looked at a brief example here. You can walk through this one in a little bit more detail on your own if you want, but ultimately all it's trying to show is that to get that reaction to happen, you have to have the proper orientation of those molecules. So what they're doing is they're tweaking the orientation of those molecules and saying, look, no reaction happens here. No reaction happens here because it didn't have that orientation. Kind of, sort of? Okay. Which gets us to our energy diagram. We've got a chemical reaction here. I believe this is where we ended. What you all should be able to go through and do for this particular reaction is to draw an energy diagram. Theoretically, you spend some time looking at this. If we go through and draw one, okay, you should be getting used to these things. You're starting to recognize that it's going to be hard to remember all the little individual pieces that go with it. I need to draw. So we could draw an energy diagram. Our energy diagram has our reactants, has our product, and our transition state. Okay? We could label those as points. It's a little bit dramatic to call them points, okay, because the reactant is anywhere in the well to the left, and the product is anywhere to the well to the right. The transition state is the peak, but it's not really a point. It's transitioning. Okay? You're giving me a weird face. Why are you giving me a weird face?
Well,
did I make a mistake?
No, I drew it as the product side is lower because it's exothermic.
So did I make a mistake?
So, I think so.
Yeah, I made a mistake. So when we go through and do this, those are those individual points. That's great, we've got that, but there's more information we can stack into this, okay? One of your classmates started going after activation energy, which is good to point out where it is. The activation energy is where you're starting to the transition state. Typically, where do we start? With the reactants, so that's where we're looking at that difference, right? What we'll introduce later on is a concept of reversibility in our reactions, and now we've got weird things going into play. But typically, we're looking left to right. Our activation energy is the difference between the reactant and the transition state, okay? That's a hard energy to quantify. We would need a lot of extra pieces of information to quantify it. So as long as it's there, you're okay. The next one that we have to worry about is the delta H. How did you calculate delta H? Exactly right. You take the energy of your products, which I'm just going to call E, products minus the energy of your reactants. And if we look at our diagram, remember the y-axis is our energies. So what we're saying is the product energy on this drawing is higher than the reactant energy. What is that going to result in when we run the calculation for our delta H? A positive value. A positive value would be endothermic, not exothermic, which means, yes, indeed, I goofed in drawing this. And what we would need to go through and do is adjust our diagram to ensure that we get a negative value. The product energy has to be drawn below the reactant energy. Okay? The delta H is now the difference between those. And what we'll discuss as you continue through the semester is that that's not truly the delta H. It's just a good first approximation. Okay? So that now better represents the information we're given. Okay? Test-taking things. Okay, we saw the first one was clearly wrong, right? Product energy was higher than the reactant. We okay with that? Cool. Is the product energy lower or higher than the reactant? Because if I draw a dotted line from the reactant, I think it looks lower. If you draw this on a test, you've now made it ambiguous for the grader. Okay? Is that a good place to be? No. Okay, so if you know it's exothermic, max that crap out. Okay? Make it obvious to the grader that that's what you're trying to show. If it's endothermic, make it endothermic. Okay? If it's supposed to be equal, make it as close to equal as possible and then add a little note. R equals P. Make sense? You're creating a defensible position to get as much credit as possible. Good? For the sake of time, sorry, silence is going to become a yes. I don't really like that, but we're going to work with that. Do you think that the enthalpy change for a reaction, endothermic or exothermic, affects the rate? Talk at your table. Okay, so let's look at a picture. We ready for a picture? Yeah, thank you. Love the yeses. Cool, here's a reaction. Very exothermic. What controls the speed of this reaction? Half right. What controls the speed of the reaction? What energy? What? Half right. The activation energy, okay, which is the difference between the transition state and the reactant. That's why I told you guys half right, because you gave me half of the equation. Okay? This is your activation energy. That's what controls the speed of the reaction. That's it. Okay? What happens, because this is now an what? Endo or exothermic reaction? Exo. Fantastic. Whoop. Let's make it endo. Did the reaction go any slower or faster? No, it has no effect on it. Okay? The energy of your products has no effect on the speed of the, at least forward reaction. Okay? The only thing that matters is the difference in energy between your reactant and your transition state. That's a little mind-boggling and weird. Go back to our very first lecture and look back at the notes where we drew an energy diagram and I said this part is kinetics and this part is thermodynamics. The kinetics is all about speed. It's only those 2 points. Okay? Tricky. Pay attention to that. It simplifies things for us because now I don't have to look at 3 data points. I really only need 2 to think about the speed of the reaction. That's kind of neat. Questions about that? Was that questions over here? You guys good? Okay. You're free to like mumble to yourselves. That's fine. But when I hear it, I'm going to ask. What would the energy profile diagram look like for an endothermic reaction? Label your activation energy and your enthalpy change. Okay. We kind of already did this, so I'll go through and do it real fast. Is that okay, or do you guys want time? Good. Okay. Reactant, product. Okay. If I want endothermic, the products need to be higher than my reactants so that when I calculate my delta H, I get product energy, which was big, minus the reactant energy, which is small. That's going to be a positive value. Yeah? It was fast. Okay. That gets me my endothermic. It also says to go through and label activation energy and enthalpy change. This one, the endothermics get a little bit kind of over-labeled. Like things fall over top of each other. You get your activation energy is the difference between your reactant energy and your transition state. And then your delta H, as we've already shown here, your enthalpy is looking at the product versus reactant. I think we answered all the questions. Good? Feeling a little better about it? Do you have questions? Are you sure? Okay. And I walked away from the computer and I can't hit next on the screen. Okay, which then takes us to pictures. Yay, it's like a high jump. Okay? You can't like freeze the high jumper in the air. It doesn't work. Okay? They can exist at the bottom before the jump and they can exist on the pad after the jump. They're transitioning across. They're in motion across those 2 points, but I can't freeze them there. I can't just say, oh, you're at the top. Just stop for me up there. It doesn't happen. It's a transition point all the way through. Okay? Molecules must collide with enough activation energy. Draw a graph showing the distribution of kinetic energy among a sample of molecules. Okay? Full disclosure, I should not record this. I don't know what I would have drawn. Does anybody know what you would have drawn? Like I see the answer, like I know what it's supposed to be, and I go like, oh, okay, that makes sense. Okay. What we're talking about is a sample, fraction of molecules, a whole bunch of people in this room. Okay? And we want to look at the kinetic energy of all of those particles. So if we add up each of those kind of particles, it's a histogram effectively, where I look at each of those energies and I add up all those particles, I'm going to get the sum total. Kind of make sense? So I can never max out. I can't have 100% of the fractions. So does it make sense when I look at a sample that 100% of my particles all have no energy? No, why not? That's a good strategy for exams. You can't get 100% on an exam. Okay. Particles. Why can't you get 100% of your particles with no energy?
They move it around and interact with each other.
What allows them to move? Heat. When are we going to get zero kinetic energy?
Absolute zero.
Absolute zero, which we're not allowed to get. Okay? So laws of physics step in the way and say you can't do this. Okay? Which means at no point are we ever just going to get a plot where it's just whoop. Doing black on black was a bad idea. There we go, red. Okay, with zero particles. would it make sense that if I provided enough heat, so they're all moving around, that every single particle would have maximum kinetic energy? No. Why not?
Because they're not all subject to the same temperature. I mean, heat to some degree,
Yeah.
because there are going to be fluctuations in temperature, so they're not all going to be subject to the same amount.
What happens when two particles with the exact same kinetic energy collide and hit each other?
Bounce off each other.
If they have the same kinetic energy
Is the test.
and the same mass, they stop. Their motion completely cancels out. So even at high energies, you are going to have some particles that aren't moving because they've been hit. Okay? Sometimes, depending on the mass and the energy and all of that, they'll be hit in a way that they continue their kinetic energy on. But there is a finite probability that they stop, which means at some point, regardless of the energy in our system, we will have some particles down here. Histogram. Okay? How likely is it at high temperatures, how likely is it going to be that we have very few particles down there? Really, really low. So we might predict this to be really, really low. And then we start to see particles increase in population, right? Histogram. And then what starts to happen? It's going to go back down. For the same reason that we would expect very few particles to have low energy, we'll encounter the same system. We expect very few particles to have maximal energy. And what we get is effectively a bell curve. What happens if I heat up the sample? If I heat up the sample, kinetic energy can go up. What's going to happen is kind of a slide, but we're not taking the absolute curve and moving the whole thing. All we're doing is taking the maximal energy, and we slide that one, because we'll always have some particles with zero. So with higher energy, I'm going to start to see some out here, and what we'll see is my peak, very crudely, I drew that horribly, but hopefully you get the idea. Okay? Your peak kind of slides a little bit. Does that make sense? And so this all looks gross as a histogram, but that's effectively what we're trying to show when we move to a real diagram. This is showing now that curve. That curve is the distribution of particles. The vast majority of our particles are going to be in this large peak. If we look at running a standard chemical reaction, your activation energy is the energy necessary for the reaction to run. Almost universally, your activation energy is only trapping the top portion of your particle population. Right? And you can change the mechanism and drop that activation energy a little bit, but for the most part, you're only looking at that top portion. This is why when you add heat, you get more product, potentially a faster reaction, because this curve flattens out a little bit, and it brings in a slightly larger population of particles. Kind of, sort of? Officially, what we talked about is like next week's lecture, a little bit. Okay? So, higher activation, slower rate. Right? Higher activation energy means there's fewer particles that actually have enough energy to run the reaction. And if there's fewer particles, that's a slower concentration. Okay? So if we go through and look at this, okay, we have an overall reaction. We're taking O3 and it's becoming 3O2. Okay? And I shouldn't walk away from the microphone. Okay? That overall reaction can happen a variety of ways. The how it happens is our mechanism. Okay? That mechanism is being shown down here, step 1 and step 2. Okay? Step 1 is the first step of that mechanism. Step 2 is the second step of that mechanism. How are my mechanisms different from my reaction?
Can you ask that again?
When I look at this reaction, how is it different than my mechanisms?
There's less molecules.
That's unfortunately characteristically here. It's a really crappy question to ask. There's virtually no visible difference between these. Okay? There is some information that allows us to know that we're looking at the overall reaction and not mechanistic steps. How do you know the top one is the overall reaction? Yep. You're like, that's dumb. I shouldn't have had to say that. Yeah. It's the overall reaction. It says it's the overall reaction. How do we know the other reactions? Because they're still reactant, arrow, product. How do we know those are mechanistic steps? It's equally dumb.
The product of one step is used in the reaction of the
Okay.
next.
That's a really, really nuanced look, which is fantastic. Also not always the case, but if you look at your steps, this product is used down here. Okay? And if that was an overall reaction, it would be done with the products. So we could tie these two steps to each other as mechanistic steps, which is a phenomenal thing to look at. That's also really hard to pull out of it. So good job. There's an easier way to know that we're looking at mechanistic steps here.
Step one, step
It says step 1, step 2, yes. Okay? You don't have to make it more difficult. What you did was great. I love it. But look for those word clues to help clue you in that what specifically you're looking at. Does that make sense? Okay. Which sets us up with a question. Draw the energy profile diagram for this mechanism. Okay? So I want another energy diagram, but I want you to draw it so that it represents the mechanism for this overall reaction. Pause the video again. This is going to be something you guys are going to work on a little bit. Cool. We're starting to pick up some words and some talking through this. I heard some people laughing and just being like, I'm just doing a little. Okay? Which makes a whole lot more sense if you saw what I was doing instead of actually looking at the recording.
Oh, you're right.
Okay? But what we're looking at is how do we navigate this? Our energy diagram is for the overall reactant, or reaction. Okay? That's the top. We have reactant transitioning to product. Okay? So the reflex that a lot of people will jump on is, ta-da, I did it.
What do we have to?
What?
What do we have to like transition from?
Right? But is that how the reaction happened? We can look at our steps and say, I have reactant, yep, and then what happened to it? Is that product? No. So if we look at that first step, I'm going from reactant to something that is not the product. Okay? Which means I can't go like that. I have to go to something. Okay? So in another conversation, we just called it a thing. We did a reaction, and it went to a thing, so we called it T. Okay? I believe we actually talked about what this is actually called, again, last week, but I could be wrong. We'll see. Okay? So we had to do that reaction. That would correspond to step 1, with the transition state and all of that. Then what did we do with that thing? That thing did another reaction. So it reacted and it made more things, except those things were the actual product. This is now step 2. Right? Within each of those steps, you have different speeds of the reaction. What dictates the speed of each of those steps? The activation energy. Where's the activation energy for step 1? I just want to know where it is on my diagram. How would I draw it? What?
From like the R to step 1.
From R, I forgot I labeled it as step 1. That would be the speed for step 1. Where's the speed for step 2?
Transition step 2.
Don't call it transition. This is the problem with using T. Right?
From T to step
From T, or what we were calling thing, to step 2. That's that difference. Okay? What dictates the speed? Well, how big that step is. Admittedly, I drew these arrows a little bit goofy, but if we look at the sizes and magnitude, are those sizes kind of close to each other? Yeah, which would mean which one was faster if they have the same magnitude activation energy? Good answer, neither of them. Okay? They would have the same speed because they have the same activation energy. Is that what this information tells you? No. We need the first step to be slow. So what does that mean has to be true about its activation energy? It needs to be higher. Remember those people being like, dang, that's really high. How do you know it's that high? I don't. All I'm trying to do is draw it so that it is very clearly the slower of the two steps. Yes?
You always just put the thing, like, back to the bottom.
We'll talk about that in a second, too. I don't like the word thing because we already expressed that it was an issue with transition state because it's not a transition. It's not thing. We want to use a better word than thing. I thought, another T word, we talked about what we would call that. Did we talk about that? Oh, do you remember? Did I not talk?
You talked about the intermediate.
Cool. It's an intermediate. And intermediate conveniently begins with I. So we can stop calling it T, okay, because that's just going to be obnoxious and we're going to refer to it as I. Okay, for intermediate. Okay, now, wait. I didn't answer her question yet. Can I answer her question first? Okay, cool. Which brings up an interesting point. Within this, what did the question give us information about? About the placement of any of those points, what did the question give us information about? Okay, it told us exothermic, which tells us the relative location of the reactant and product. Whoops, starting the wrong thing. Exothermic. What else did the question give us?
Steps are slow and fast.
Tells us slow and fast. Okay, so these two things together tell us that step 1 is bigger than step 2. Does it say how much bigger? No, absolutely not. It just says it's bigger. So when I'm going to draw it, I'm going to make dang sure that it's bigger so someone can't complain and say, well, that wasn't bigger, that looks smaller, and bust out a ruler on me. I'm going to try and accent that. Do I know how much bigger? No. All right, so I have no information about where the peak of step 1 is. I have no information necessarily about where the peak of step 2 is. I just know the relative distance between I in step 2 and R in step 1 must match this. Does that make sense? Cool. What does it tell me about I? Okay, some people actually said the answer instead of just being silent. That's awesome. Nothing. It tells me nothing about the location of step I. Okay? So I could have the I drop all the way down. I don't know that it drops all the way down. It could very well. Be up here. Does that change my answer at all? No. Transition state is still between those 2 points, right? It's still smaller for step 2. So where should I place I?
Doesn't matter.
At this stage, you don't know. So place it and hope for the best. Okay? If you lose points, then you can come back to this video because it's recorded and you can be like, but Mike said. I hope that doesn't have to happen, but whatever. Okay? How would we know where to place I? Because I will tell you, I think it should be here, not down here. And I would argue you sort of kind of have the knowledge. I is referencing the intermediate. Oxygen atom. How common is oxygen atom? It's not. It's not common at all. Because when we say oxygen, what are we referencing? O2, not oxygen atom. So oxygen atom is insanely uncommon. Why?
It comes in O2.
It's high energy. That's why. So with that bit of information, I know that I want to place my intermediate higher than my reactant. Because the reactant of ozone, I've seen that. That's a reactant. I can control that. Oxygen atom, I never actually touch in the course of this reaction. It's produced and consumed. I have no information about it. Okay? So can you draw that information out of this? Yeah, that requires a lot more chemical knowledge. Do you have that? Are you expected to know that? I would argue no to both those statements. Okay? And if it comes down to it, yeah, I'll defend you. Doesn't mean I'll win, but I'll defend you. Does that answer your question somewhat satisfactorily?
Kind of different topic, but that thing we made, is that a synthesis?
So if we're looking at this overall reaction, we could call this a synthesis. What was this the synthesis of? It's the overall reaction. This was the synthesis of oxygen gas, O2. Is the intermediate a synthesis? No, because the synthesis has to exist. I make something so that it's there, so I can say, yay, I made it. The intermediate isn't something I can say, yay, I made. I never know exactly how much is there, because it is both being produced, concentration goes up, and consumed, concentration goes down. Where does it balance out? That becomes a much harder question to go through and answer, and one that becomes challenging potentially later on in this lecture. Ish? Cool. I talk too much. We're supposed to laugh at that. That's good. Okay, so Tuesday, Wednesday, week 2, we just talked about the enthalpy change for a reaction. This is her summary slide, so we have now caught up to where we were supposed to be at the end of last week. Make sense? Okay. Rate of reaction is dependent on our concentration, okay, or our molarity over time. Okay, so we're looking at molarity per second. Why did we want seconds? Fast. Okay, we want our reactions to happen on a fast scale so we can get out of the lab faster. Okay, so we're typically looking at experiments that run per second, not in other values. Admittedly, it's a ratio, and you can control both the top and the bottom. So if the molarity has a small change, you're going to get a small rate. Okay? So if we look at these two solutions, all that we're saying is we have more particles in solution 2. What would we expect to happen to the rate? What happens to the rate of a reaction if you increase the amount of particles present? It should increase. Yes. Okay? So for our reaction to occur, we have to have orientation and enough energy. Does increasing the concentration of the reactants affect the reaction rate? Yeah, we just answered that. Why?
That increases the rate of reaction.
So let's walk through that again. Let's be careful with that. Okay? What happens when you increase the concentration of does it affect the rate? We said the rate is affected by increasing the concentration, and the why was because it affects the rate. That's a little circular. Do better.
There's more reactants to react in the reaction. More molecules.
Why? The answer's on the screen.
More collisions.
More collisions. Okay? You increase the number of collisions. That increases the odds that you're hitting proper orientation. Does that make sense? I would say the same thing as you do. Okay? This goes back to our collision theory. Okay? So if the concentration of our reactants double, what happens to the rate of the reaction? Okay, so this becomes fun. Okay? Let's go slowly into this. Okay? What did we do to the concentration of the reactants? Simpler, not doubled. Simpler. Increased. What should happen to the rate of the reaction? It should increase. So if we double it, we're now adding a quantification factor. So now we go, oh, well, it doubles. Does it? Okay. So does it say the same? Absolutely not. That makes no sense. Doubles. Okay, yeah, there we go. There's a good answer choice, except why does it have a question mark? That's a little weird. Does it quadruple? No, I would never do that. Why is there a question mark? Or does it depend? Unfortunately, it depends. Okay? What does it depend on? Okay? That becomes kind of the next part. That depends on how the reaction happens and our rate law. The rate law is an equation that tells us how the rate of the reaction depends on the concentration of the reactants. So when we talk through our reactions, our rate increases when the rate increases. That would be defined as a direct relationship. All right, so you could go through if we really wanted to. I don't know if she's used notations like this. Admittedly, I did not use this notation for the Tuesday class. Rate and concentration are directly proportional, so you can use this little alpha symbol if you've seen that in mathematics classes. It's not an alpha symbol, but close enough. Okay, saying they're directly proportional, which is nice because then if you factor in some other pieces of information, like any constants, was there any constants that we needed to be concerned about when we talked about our chemical reaction? Was it just how many pens and caps I've got floating around? What else mattered? The orientation also matters. So there's an orientation factor that we said was going to be, begins with a C, constant for any given chemical reaction. I also have to factor that into my equation. Guess what K is? A really bad way to spell the word constant. K is a constant, and that constant factors in some of those other pieces of information, the orientation, the activation energy. K envelops some of that information. So we'll look at that later when we want to quantify it. Okay? But then the last thing, what the heck is that X?
I think that's the power of the reaction, like the steps or order,
Okay?
something like that.
Something like that. So maybe reading ahead. So that X is what we would call the order of the reaction. Okay? Or the order, not of the reaction, of the reactant that we're directly referencing. Okay? Which is a fancy way of just saying we've invented a language to describe what this thing is mathematically. Okay? The way that I look at it is how important is that reactant to the overall reaction? If it's really important, I would increase the number. If it's not important, I would decrease the number, more or less. Okay? To give an idea of potential examples of what could happen, this is now looking at our mechanisms. A first order reaction is the molecule collides, okay? Or sorry, no collision. The molecule doesn't need a collision to react. It goes poop. Doesn't go poop, but pop. Sorry. Again, I thought that was funnier. Okay? Pops apart, and we get potential intermediates. So if we were going to look at this as a reaction, our rate would be equal to our rate constant, okay, all those constant things, times the concentration of my reactant, those two balls. Okay? And the order for this, how many, because we're looking at a mechanistic step now, how many of those particles did I need for this reaction to occur? Thank you for showing me a nice finger. Is 1. So the order for that mechanistic step is 1. Okay? What happens if we switch it up? All right, I would argue the next slide is easier than this slide. What's my rate now going to be dependent on? Again, it's the mechanistic step. This is how the reaction happens. So I'm going to have my rate times my rate constant times what? What particles are necessary for this reaction to happen? Well, I need a blue particle. Do I just need one blue particle? I would need 2. And because those things in brackets are identical, what can I condense that to? That's right, I can say K, circle with a square. Now when I look at that order, that number up there is called second order because second is the same thing as 2. That's where that information is coming from. Okay? Does it have to be the same type of particle? I could have 2 different particles collide. Same process. Is this going to get me a 2? You say no? Yeah, no. Why are you saying no?
Because they're two different ones. It's like,
Yeah. So it's just a 1 and a 1. How does that get me second order? The order for our reaction is the sum of the order for each of the individual reactants. 1 plus 1 is conveniently 2. The overall reaction is second order. What is the order with respect to the green reactant? 1. So depending on how you phrase the question, you can look at the order for your overall reaction. That's the sum of all those exponents. Or you can look at an individual reactant and say, what's the number for that one? Okay? I heard someone talk about 3. Okay? I think in a different way, but let's go through it. How about I add another particle? Could I then go through and get a third order reaction? Yeah. How about a 4th? 5th? 6th? Okay. Now we've got an interesting dilemma. Where does this stop? Because do you really want to deal with the rate equals k of something to the 1,000th power because it showed up 1,000 times? That's going to be painful for our calculators to deal with, right? Never mind our brains. Is there a limit on this? Okay. This goes back to what the mechanism means. The mechanism is saying all of those reactants have to collide. So what are the likelihoods that I'm going to get 1,000 particles to all simultaneously collide at the exact same instant to make the product? Ooh, very low, which means 1,000 doesn't make sense. Right? How about 100? I'm going to run the same joke again because I thought it was funny. Take one down, pass it around. How about 99? Take one down, pass it around. 98. You're not saying anything. Is that because the joke was dumb or because you're like, no, I'm just going to keep saying no? Well, when are you going to say yes? How many particles is it reasonable for me to expect could collide instantaneously to produce a product? 10? 9? 32 and a half. Okay? That's hard to kind of figure out. So what we can do is back extrapolate this out to people, because people are effectively the same thing. Okay? We're talking about people producing products. An individual person could have their arm fall off, and there we go, products. Okay? 2 people could collide and produce a product. Kids, yay. Okay? What are the odds I get 3 people coming together to complete something successfully?
pretty high.
Pretty high? How many partners are in your lab group?
2.
You actually have a 3-person group?
No, 2.
There's 2 people in your lab group. Why are there only 2 and not 3? Because 3 sucks. What happens if you have 3 people in your lab group? 1 person does, 1 person writes, and 1 person watches. That's not a successful lab group. If we run 3 reactions, what happens? Green and blue come together, do their thing, and the red one watches. Okay, like the ACF safety video. Right? Some people might get that. Okay? The red one isn't doing anything until after the green one and the blue one do something. 3 particles is insanely unlikely. You can use your imagination and think about relationships. Single people, there's tons of single people in the world. Couples, there's fewer, but we get successful couples. How successfully do we get 3 groups of people in a successful, nurturing relationship?
You hear about it.
Okay. You hear about it, maybe. And even then, they're probably lying. Right? It's not making judgments necessarily, but the odds of that successfully working are very slim. We run back to our chemical reactions. If the odds are very slim, does it make sense to create a mathematical expression that would explain that to exist? No, it doesn't. So when we talk about the orders of reactions, we really get first and second order. We don't go higher. Could we get lower? What's lower than 1? Good answer. 0. Nothing. Could a reactant not be involved in the chemical reaction? Yeah. Multiple steps. You could have a reactant that's involved later or in a fast step after a slow step, which would then mean its order in the reaction, its importance for the reaction to occur is non-existent. It's a zero-order reaction. Right? So when we're looking at the rates of our chemical reactions, we can get some kind of odd things coming out of them. And that's why we have to study our reactants a little bit, or our overall reactions better. Okay? So we want to write a rate law for this reaction. Take a swing. See what you come up with. Talk to the people around you. Rate law for this reaction. What are we looking at? Okay. So we'll walk through it. We'll walk through some kind of initial places to run this first. We could go through and say, well, it says for the reaction, so what am I going to look at? I'm going to look at the reaction, and I'm going to say, oh, my rate law is O3 to the second power. Right? Whoa, where'd you get the 2 from?
There's 2 of them.
There was 2 of them in the reaction. What was that 2 dependent on? The order. And what was the order in reference to? Went by fast. It's okay. The how the reaction happened. How does a reaction happen? What do we look at?
Steps.
All except steps. We look at the mechanism. So if I write that out, really all I'm saying is that I don't know what that order is. That order is dependent on the mechanism for my chemical reaction. Okay? It has to be dependent on ozone, because ozone is my reactant. There is only one reactant. It has to be ozone. But what is that order? That order is mechanism dependent. How does the mechanism work? Right? To figure that out, I have to have more context. I have to have a mechanism to look at. So I could go back and now look at the mechanisms underneath it. Which of those 2 steps is the most important mechanism for me to evaluate? Step 1. And if I talk to the answer to you, keep your mouth shut. Why is step 1? It's step 1 because it's the slow step. That's the only step I care about. If it happens fast, that's not going to control the speed of my reaction because it's happening fast. The only thing that's going to control the speed of my reaction is the slowest step. So if I'm now evaluating my mechanism, all I care about is what's happening in step 1. It's the slow step. It dictates the speed of my reaction. So I would now go through, so this would be my overall. That says overall, trust me. And I could look at step 1, and I would say my rate was equal to K. What's the reactant? Ozone. How many of them are there? 1. Okay. This order is now dictated by my step 1 rate. That kind of? Sort of? So what's my rate law? Rate equals K times ozone to the first power. I don't need 2 ozones to make this reaction happen. I need 1 ozone to sit there and be like, pop in half. So I have that oxygen atom to be able to go through and run the next chemical reaction. Can I break you? Of course I can. Why not? We'll just say that was rhetorical because you didn't answer. For the record, if you had said no, I still would have done this. Sometimes no answer you say matters. Now what happens to my rate law? What changed? Elaborate, because step didn't change.
The speeds of the steps.
The speeds of the steps changed. So now for my overall reaction, I'm going to be dictated based off of the speed of step 2. So what's the rate law for step 2?
Okay.
Okay, and all of those would be first order. So we could go through and drop the ones in. Okay, if you need that extra information, do so. It doesn't hurt to put it there. Okay. What would be the overall order for the reaction? Second order. Cool. Is this rate law useful? It's a dodgy question. What was our last rate law? When we exchanged those back and forth, our rate law was equal to K times O3. Because, I mean, in all fairness, right? I didn't ask if that one was useful. So we go back. Is the red one useful, where we had the slow step first? Is that useful as a rate law? Why is it useful? Okay. Depicts the rate of the reaction. Is the second one useful? Yes. Why? It depicts the rate of the reaction. Okay. How would you calculate the rate of the reaction up here? What do you need to know in red? What do you need to know to calculate the rate of the reaction? You need to know the rate constant. Cool. What else do you need to know?
Energy from 3.
That's not energy. I don't know where you're getting energy from. Concentration. Remember, our brackets meant concentration.
Yeah, that's right.
Okay? Should I be expected to know the concentration of O3? And this is one that people are like, I don't know, what do you mean? Well, what's the overall reaction? I take 2O3 and it becomes 3O2. Should I be expected to know how much reactant I put into a reaction? Yes. That's why you're running the reaction. You put that stuff there to make a study of this. Okay? You absolutely should know the concentration of reactant. You should equally know concentration of product. How do you know you actually did a reaction if you don't know the product's there? So both of those should be definable by you, the chemist. Okay? So the red one, yes, perfectly makes sense. Black one, we say, oh, perfectly makes sense. I should be able to calculate it. Do I know the concentration of O3? Do I know the concentration of O? Where was O? O was the intermediate. So the concentration during the course of the reaction is? At the start of the reaction, it's 0. At some point later in the reaction, it goes where? It goes up. And then it goes down. Depending at where we're at in the reaction, we're getting that concentration going both up and down. At some point, it'll reach a steady state. And if we're lucky, we could monitor it. But the vast majority of scenarios, you will never be able to monitor the concentration of the intermediate because it's effectively a transition point along the way. It's unstable. I make it and I destroy it. So is it there? Is it not there? I don't know. And if you don't know if it's there, is this a useful rate law? No. Ooh. Okay. If that ends up being the scenario, we have to change how we reference our overall reactions. Okay? It is not later on in the slides, but it may be later on, well, in today's slides, but it may be later on next week. Okay? And we'll go back and look at this, potentially. It's going to depend on what Dr. Schneblin wants. Okay? What happens on how we would figure out, at least mathematically create a system where we could figure out the concentration of oxygen atom, concentration of our intermediates. It's a challenging question to differentiate. What we would hope is that we don't have to worry about it. Okay? When we cross that bridge, or when we get to that bridge, we'll cross it. I just wanted to point it out. Okay? So what happens to the rate if the reaction of O3 is doubled? What did we say the rate of our reaction was? Yeah? So what happens if I double the concentration of O3? What happens to this value if I make this twice as large? It doubles. Does that make sense? Okay. What happens to the rate if this goes up by 4 times? Quadruples. Okay. Another quick test. We're going to erase that mechanism and we're going to say 1, mechanistic step. If it is one mechanistic step now, new question, what's my rate law?
Let's see.
It would be the second order.
Because I'm now looking at it as one mechanistic step, that thing has to happen all at once, which means I need to take two O3s and smash them together to produce my oxygens. That's two of those particles have to come together to create it. We're changing how the mechanism happens. And if we change how the mechanism happens, what happens to our rate law? Also changes. And by changing it, we're going to put it second order now. Okay, you got it. Do you get it? Because you volunteered and said it stayed the same and it did not. Do you understand why it doubles now? Or why we have to put that, not doubles, why the second exponent? Everybody okay with that? We changed to an entirely new mechanism. It's a different question. Okay. Blue box. What happens to the rate of the reaction if O3 is doubled? Okay, does everybody want to live and die by this gentleman?
No.
You don't even want to live and die by your own words? All right, we got another doubled. Do I hear another doubled? Going once, twice, too late. If I make this 2 times as large, what happens to that? 2 to the second power means the rate quadruples. So changing the concentration can quadruple. It depends on the order, the mechanism for the overall reaction. You gotta watch for that. Does that make sense? Okay. What? Did someone say what's quadrupled?
Yeah.
4 times.
No, like, just so I can write out the answer of what would happen to the rate. Oh, the rate is quadrupled.
The rate was quadrupled, yeah. Rate law for this reaction. You guys are rock stars at this. Oh, I'm going to say something else controversial. Okay? Do you all have these slides?
Yes.
The answer is yes, you all have these slides. Okay? I can't stress enough how many times I see this. It's just go, oh, I'm just writing down the question. You are wasting your time. Do not write down the question because you have the question already. By writing it again, you've wasted all of your time. Does that make sense? Okay. What's the rate law? Where do we start? Rate equals. Okay, awesome. Now the hard part. Work on the hard part. If you don't have the slides handy, you can always tag the slide number. I did put the slide numbers on them. What's our rate law? Rate equals K. Whoops, HI squared. You brought in the 2. Why could you bring in the 2? Was that a what the heck? Did I just see that? Okay, just curious.
Because it was 2, and it's a single order, or a single step.
Okay, I'm going to break up your statement into 2 things. You did a great job. For this one, we set our rate law, K03, and it was first order, right? That's what we saw. Could we bring the 2 in? No, we couldn't bring the 2 down. So when you say, because I looked at the reaction, it showed 2, I'm going to say that's BS. Because the last reaction had a 2, and I couldn't bring the 2 down. You then followed it with the more important statement. What was the more important statement? Yeah, there it is. It's a one-step mechanism. Okay? So when we looked at the ozone, we were saying this is a reaction, and the mechanism is what follows. We have to use the mechanism to predict it. In this case, we are told that this is the mechanism. Now we can pull those coefficients in. Make sense? You've been provided that extra context. That's why you're allowed to put that 2 in. Okay? Now what happens, bless you. Now what happens when you double the concentration of HI? It quadruples. What happens if you triple it? Okay. It's sextuples, okay, which is fantastic. That's a fancy way of trying to say it goes up by 6 times. This gentleman over here thinks you are incorrect.
Well, it would be 9, my bad.
Why is it 9, not 6?
Because 3 squared is 9.
It's a squaring factor. 3 squared is 9. Does everybody see that? Watch out for that. It's real easy to fall into a trap of accidentally multiplying it. That's why it's asked, actually. Okay? Make sense? We got it? We're good? We're awesome? We love it? Cool. So how do we find out the rate law if we don't know the mechanism? Okay? Because if we just have the equation, I just say, here's the equation. How do I know what the order is supposed to be? Okay? Well, I have to go to an experiment. Okay? And in that experiment, I'm going to start tweaking the concentrations of each of the reactants and seeing how that change affects the rate of my reaction. Okay? So what I'll end up doing is measuring the initial rate of the reaction, so right after combining reactants. Okay? How do I know a reaction has happened? Right? This goes back to 151. You're looking for something visible that you can tangibly grab a hold of. Color changes, formation of solids. You can look at gas or pressure. You can look at spectroscopy. I don't think you guys have seen any spectroscopy, so that's just a foreign word to you. Okay? But those are pretty much our standard ways of doing it. And then what we do is we say, well, when I change the concentration, how did that affect my rate? And I design an experiment that allows me to make those comparisons relatively quickly. Okay? This one we're going to hit real fast. Okay? Doesn't have any context on it, but if we're trying to determine the rate change in concentration over time, how do we calculate that? Okay, let's look at concentration of product. How would I calculate the rate change? I would look at the change, delta, of my concentration of product over my delta time. What does delta mean? How do I calculate that?
Final minus initial.
There it is. Time final, time initial. I'll fix that in just a little bit. Those are T's. Time, and then you usually see a subscript referencing the final. How do you calculate your change in product concentration? There you go. The concentration of my product, final, minus the concentration of my product, initial. Is this something you would be expected to do in an exam in class? Probably not. Where are you expected to do this? Lab. Okay? You will do a kinetics lab, and one of the things that you're going to be doing is generating effectively the data table we're about to look at. Kind of, sort of? Okay. So, what we would go through and do, wow, I feel kind of excited about this. That's pretty good. Pretty good job, Mike. Yay, me. Okay, catching up pretty well. What is the order for the CH3CBr? Okay, so now I'm not looking at the overall order for the reaction, so I could look at that. I'm very specifically being asked for the order for a specific reagent and for the other reagent. Right? How do I go about doing this? Okay, so we can call this experiment 1, 2, and 3. So what we said is we wanted to change. We want to see how those systems change when I make those concentration changes. So let's take a look at experiment 2 and experiment 3. So I don't care about 1. What happened to the concentration of my CH3 thing? Okay, depending on how you want to look at it, you could go it doubled or it halved. Okay, or it increased or decreased. Really all I want is it changed. Right? It changed. What happened to the concentration of hydroxide? It changed. What happened to my rate? It changed. Why did the rate change? Which reactant affected the rate? So one reflex is, both did because they both changed. Is that true? Not necessarily. They could both affect it, or maybe only one is affecting it. I haven't controlled my variables. I don't know why a change is happening. That's bad science. So comparing experiment 2 to 3 is a really bad idea. But if I switch it up and say, well, that was the wrong button, let's try that one. Let's compare experiment 1 to 3. Now what happens? I leave my concentration for my CH3 constant. And if it stays constant, should it affect the rate? No, because it didn't change. What happened to the concentration of my hydroxide? It changed. What happened to my rate? Ooh. So is my hydroxide affecting the rate of my reaction? No. So if we went to look at an overall reaction for this, I know I'm out of time. There's a K in front of that. Okay, and we'll call it X and Y. Are we okay with that? Because we don't know what those are. We would have to determine those. Okay, so what we did is picked an experiment where this term, the CH3 thing, is irrelevant because it's not changing. And what we're really looking at is what happens with the hydroxide, because it changed. If this value changes, what should happen to the rate? Theoretically, it would change if that Y value was non-zero. Did the rate change? What does that mean the Y value is? 0. By comparing experiments 1 and 3, I know the order with respect to the hydroxide. I know it's 0. It's irrelevant to the overall equation, which means when I hold it to the 0 power, what number do I get? 1. It has 0 effect or a constant effect on the overall reaction. So that drops out. How do I figure out X? Compare reactions 1 and 2. With that, we are done, but what this is going to produce is going to give you a rate law. With this rate law, what we'll then do on Monday, okay, is we'll look at 2 mechanisms and say which of these mechanisms explains that rate law best. Okay? We'll then go through and say, well, how can we figure out the rate constant? Okay? I want you to spend the time to work on that. Remember, we're behind. We need a little bit of catch up. How far behind are we? Not that bad. We caught back up pretty much. No excitement. Whatever.